Hi, in this video, we want to take a look at some calculations that are used in regression to estimate parameters, to perform diagnostics, to check that our model is a good fit. You know, the type of calculations that usually like Python just does it under the hood. What we want to do it like the under the hood way, the quick and easy way, but then we also want to do the calculations manually so we get a better feel for how these calculations are done, and so that we have deeper understanding into what they mean and what's going on. All right, so once again, we are using an introduction to statistics with Python, and here's the website for the code that I'm using. So let's go ahead and let's start loading our packages. So we're going to get NumPy, Pandas, Matplotlib, and now we're going to be getting into stat models. So, you know, we're going to use the formula aspect of stat models. Let's go ahead and get some linear regression from scikit-learn, and then let's get SciPy. We want the stats aspect. All right, so now let's go ahead and pull in the data. All right, there we go. Let's go ahead and keep the plots going. I already made the scatter plot. So here's a scatter plot of our data. And we can see that there's kind of maybe a linear relationship between tobacco and alcohol. So, you know, let's go ahead and start analyzing this. And, you know, so we have tobacco and alcohol data for a collection of, you know, parts of, you know, the UK. All right, so let's go ahead, and another way to get the data in, pull it in as a data frame. So let's take a look at what the data frame looks like. There we go. Here's a region. Here's the alcohol count, measurement and the tobacco measurement. And now let's go ahead and plot the data. And, you know, the same plot as I plotted a moment ago. We kind of see a little bit of a, you know, linear term. Oh, now down here is something a little bit different. So one of them, the one that has, you know, the most or nearly the most tobacco, has the least alcohol. Well, that's kind of interesting. Which one is that? All right, so we have the most tobacco. Which one is that? So that's what? 4.56. And then we have the least alcohol, and that is Northern Ireland. Okay. I guess they use tobacco more and drink less. Kind of interesting. Okay, so and this kind of stands out to me if I was running like if I was more involved in like the data collection of this, instead of using someone else's data, I would go ahead and double check that value to make sure that it's correct, since it's deviating so much from what I see as the overall trend. All right, now, something about regression models. When you see a scatter plot like this and you're trying to fit a line, a good rule of thumb is if you can move one point around and you don't see like a linear trend anymore, then you probably don't have a regression model. Like, or a regression model probably is not appropriate. So conceptually, imagine that if I took this point right here and I moved it somewhere else on the scatter plot. And you know, imagine it with your mind's eye, and if moving that around changes it so that you no longer see a straight line trend between the independent variable and the dependent variable, you want to be cautious when using a linear regression model. And here, this is honestly kind of like borderline in my assessment, but we're going to go ahead and move forward and keep going with this. All right, so now let's go ahead and let's get an ordinary least squares model. So we're going to model out the alcohol measurement depends on tobacco. So when I do this, remember that we're going to have a y-intercept, and we're going to have tobacco as an independent variable. We're going to have a coefficient on tobacco, and the dependent variable is going to be alcohol. We're also going to have an error term that we are going to treat as a random variable that's independent for each and every observation. And here is our model. Let's take a look. All right, so I look here and I see that the p-value for the intercept is 0.07, so that's not going to be statistically significant, but we don't worry about the intercept aspect when we do regression models. Now tobacco, that's 0.007, since we're talking about the UK, that is statistically significant. All right, that's so it looks like there's something going on here. And so one thing we want to do for the rest of this video, we want to look at these individual numbers that we see throughout here, and we want to take a closer look and see what's going on. So we're interested in the numbers that we're seeing up here, numbers here, and the numbers down here for each of these. So let's go ahead and start going along. All right, so let's take a look at the F-test. The F-test tells us of our predictor variables, is at least one of our predictor variables informative to our target variable. And it's an at least one situation. We may have excess. Here we only have one predictor variable. So the F-test, if there's one that is informative, it's tobacco, because we don't have any other ones. All right, so let's go ahead and take a look. So first thing I get is number of observations, which is 10. Now, we want to look at degrees of freedom, or number of parameters, I should say. So we have two parameters. We have the intercept and the slope. And now we want to look at some degrees of freedom aspect for the parameters of the F distribution. So we've got, so if you look at the F distribution, we have two parameters. The first one for this one is 1, the second is 8. And okay, so we have two parameters, and there's always like a subtraction thing going on in statistics when we do the degrees of freedom. So 2 minus 1 is 1, and that's where we get that number 1. Okay, now how many observations do we have? Well, we have 10 observations, and and how many parameters do we have? So 10 observations, and then 2 parameters. 10 minus 2 is 8. Isn't that great? So that's where these numbers come from. So number of parameters minus 1, number of observations minus the number of parameters. Okay, those are the two values that determine the distribution of the F distribution when we run our F tests. Now remember that the F distribution deals with the ratio of variances. So when I actually get the F statistic, it's going to be some form of variance divided by some form of variance. Now let's go ahead and calculate that. And now let's go ahead and get that p-value. All right, so I go like this. Let's see. Let's take a look. All right, so our F statistic is 12.8. Okay. Now, I don't know what the p-value is. I need the p-value to really let me know what's going on. Because, I can tell you if this is a huge number, then it's going to be statistically significant. If it's a very small number, it's not statistically significant. But without using the actual distribution, I can't get the p-value. I don't know when big is big enough or small is too small. I don't know where the boundary is. Now, if I came out with 5 million, let's say just some crazy number like that, I would know it's statistically significant. I don't need to worry about the p-value. But when I'm telling Python to do work, it automatically does it for me. So let's go ahead and take a look. All right, so the p-value is 007. Hey, didn't we see that number a moment ago? It's not a coincidence. All right, so let's go ahead and take a look. And we'll go ahead and print this in a more clean manner. Here's the F statistic of 12.8 and p-value of 007. Okay, so the model is statistically significant. Now, when we say statistically significant, that means that the independent variable is accounting for some variance in the dependent variable. And that's really not a strong statement, honestly. If I need to be doing something like predictions, I need a much stronger straight line appearance here if I want to do predictions. This tells me just like roughly in general, as tobacco goes up, alcohol also goes up. All right. So another thing that we can look at when we look at regression models, we can look at likelihood. So likelihood, basically is a measurement of how well does the model fit the data, or how well does the data fit the model, depending on how you look at it. So if we have a larger likelihood, then we have a better fitting model from a statistics point of view. Likelihood and probability are two different things. So a probability tells me the likelihood of something happening that has not happened yet. Likelihood is measured on the same scale as probability, 0, 1, very natural, very intuitive to us, but there I'm measuring something that's no longer random. So for example, let's say I flip a coin and it lands and I cover it up. I don't see what it is. Now, it's heads or it's not after it lands and I cover it up. I don't know if it's heads or tails. So the probability of it being heads or tails is 0 or 1. It is or it isn't. There is no randomness involved. It's locked in. Now, how likely is it going to be heads? It's 1/2. But the probability that it's heads is either 0 or 1. I don't know which one it is. So when we say the word probability, we're talking about events that have randomness that have not already happened. They're not locked in. Once the event is like locked in, what the outcome truly is, then it's not random. We start using the term likelihood to describe like how, like to measure the, how likely something is to happen. I use the word in the definition, so it's not good English. All right, but that's why I'm in math. Okay, so here are, once again, our n is 10. Now here we have sum of squares regression. So let's go ahead and do a variance estimate, S2. All right, so we can see 0.16. Now what we're going to do, this is a formula that's in just about every single regression textbook out there. And what we want to do, we want to see what is the likelihood measurement. All right, so it's 0.0067, and it's just happenstance that it's 007. That number is not connected to the previous numbers we had. Okay, now something about probabilities and likelihoods is that these values can get really, really small. And because they're so small, we want to use logarithms to help standardize the understanding of them. All right, so logarithms. Way back in college algebra, when you were dealing with logarithms, you hated it, you didn't like it, nobody enjoys it, and you didn't understand why it's important. All right, I'm going to tell you right now why logarithms are important. Logarithms tell us the magnitude of a number. It doesn't tell us the actual value of the number, it tells us the magnitude. So it's easier to interpret numbers when I care about the magnitude, not the actual value. If you think about your chemistry classes, when you had to calculate entropy and thermodynamics and stuff like that, there were a bunch of logarithms floating around. Why was that? Well, at that point, when you were doing those calculations, you didn't care about the actual value of the number. You cared about how big the number was. Like, what was the magnitude? Like, in a ballpark idea, how much heat was coming in or going out of that reaction. All right, so let's go ahead and take a look at log of that. All right, so it's, -5. Okay. And this is on the natural log scale, base E. So statisticians generally work with base E, natural log. Most of the time, most people, prefer, log base 10 because it's more intuitive. But once you get going in mathematics, pretty quick you find that it's actually easier to do the math if you do base E. And the reason for that is because of all the calculus calculations. Even if you don't do the calculus calculations, the formulas that come from calculus are easier to work with if we keep it base E. All right, so here are the parameter estimates. So what I see here is that we have a y-intercept of 2 and a slope of 1. All right, so how do I interpret this? Well, y equals mx plus b. If, let's say that there is a country that has 0 tobacco use, then we would expect their alcohol use, on average, the average alcohol use for such a country would be 2. Okay, well, what does this 1 tell us? This 1, the slope of 1, tells us that if a country increases their tobacco use by 1, then we would expect to see, on average, alcohol consumption to increase by 1 also. So, and where I'm getting that is if tobacco increases by 1, I multiply that by the slope, which happens to be 1 in this case. 1 times 1 is 1. So alcohol consumption will increase on average by 1 if we see the tobacco increase by 1. If tobacco increased by 2, we would expect that on average, alcohol consumption will increase by 2. All right, so let's take a look at standard error. All right, so what we're doing here, we are building our design matrix. All right, so here's my independent variable, and here is the ones. So this column corresponds to the the tobacco coefficient. This column corresponds to the y-intercept. And now let's take a look at the y. So here is the target variable of alcohol. And so one way that we can do this, we can tack on 1s onto there, or we can do it like this. Go ahead and get x again. Oh, and we can use NPV stack. Let's convert that to a matrix. And so here's the same X matrix that we saw previously, but it's in a different format. And so remember that Python has different formats for different tasks, and we have to be flexible to be able to bounce between different formats as needed. All right. So let's go ahead and do some linear algebra. We're going to take an inverse. And so we don't, like in this class, we don't really need to worry about what the formulas are. We just have to understand that if we want to, we can manually compute anything that Python puts out for us. And for us, we really just want to see what the output is, but we need to have in the back of our minds where this is coming from, what's going on. And so let's take a look at what C is. All right. Take the square root. All right, and so here we have the standard error of our 2 estimates. So let's see. So remember, my first one corresponds to the intercept because the first one's all 1s. The second one corresponds to the tobacco coefficient. So here's the standard error for our y-intercept estimate. Here's the standard error for the slope of our estimate of the slope of tobacco. And so this is where we get that. And so now that if I have estimates, I have standard error, that's going to be the standard deviation for calculation, and I have a distribution, I can run hypothesis tests now. I can also get confidence intervals. So to be able to get a confidence interval, I want to get an estimate, some version of the standard deviation. So here it's standard error. So if I get standard deviation of something that I calculate, we call it standard error to make sure that we distinguish between the difference between something that we're calculating estimate and a variable standard deviation. And then lastly, but not least, I need some kind of distribution. All over in statistics, most of the time, in a lot of cases, we're going to be using the t-distribution. And the reason for that is for the central limit theorem. All right, so let's go ahead and run through this. So here we want the t statistic. So we can run a t-test. Let's go ahead and keep on going. And hey, once again, we get 007. And you'll notice that with all this code, I calculated this manually, right? And so, you know, when we saw it previously, Python did everything under the hood for us. And now we're going through and we're doing it manually. All right, now let's go ahead and get our confidence interval. All right, so here I need to pull out the estimated value, and so this part of the code, that line, gives me the estimated value of the coefficient of the y-intercept, and then I also get the standard error. So estimate, standard error, and distribution is what I need for confidence interval or hypothesis test. All right, so now let's go ahead and calculate this. And we're using this PPF with stats t. For us to be able to get the coefficient of the standard error in our confidence interval. And we can see that our confidence interval goes from negative 0.3 to 4. All right, so if I'm doing a hypothesis test, this includes 0. This interval includes 0. So at this particular value, for this value of alpha, which is our type 1 error risk tolerance of 0.05, we conclude that's not statistically significant from 0. So here, this indicates that the y-intercept is not statistically significantly different from 0. Now, most of the time, in almost all situations, we don't worry about this unless we have a reason for dropping the y-intercept. Now, I will be worrying about this on the slope of individual parameters, but the y-intercept is usually just left alone. All right, so now let's go ahead and look at our residuals. So for us to be able to do ANOVA, we need our residuals to be independent of each other. So remember, a residual is the difference between the modeled value and the observed value. And I subtract, and that gives me what the residual is. Okay, so it's the difference between the observed value and the modeled value. For us to be able to run ANOVA, analysis of variance, to get that F distribution, we need to have basically the error in the model that needs to be independent for each of the observations. We need to have constant variance, and the residuals need to be normally distributed. So what we want to do, we want to check to see, does that work out? All right, so let's look at skew and kurtosis. All right, so if I have a normal distribution that is a symmetric distribution, that means the skewness is equal to 0. Here, our residuals have a skewness of negative 0.01. That's relatively small. That's small enough that I'm not going to worry about that. Now, the kurtosis can be computed in multiple ways, 0 or 3, depending on is the normal distribution version. So this is off either way. Usually we don't worry too much about kurtosis as long as it's relatively close to a bell shape, especially with this few of points. I wouldn't be sweating that too much. All right, so let's go ahead and define some special functions to do the omnibus test for us. Now, the omnibus test is kind of like a way of measuring like the overall aspect of a model. For us, honestly, an easier way to reach the same informative value is just that F statistic. That's why I've been harping about it so much in these videos. So let's go ahead and calculate. So our omnibus value is 2.5. And so now let's go ahead and get the p-value. Okay. Now let's check to see, do we have, let's do a normal test. All right, so, all right, so K2P, yeah, there we go. So when I do a normal test, what my null hypothesis is that the distribution is equal to the normal distribution. Okay, so the distribution is equal to a normal distribution is my null hypothesis. All right, so remember, if I have a small p-value, I reject the null. If I have a larger p-value, I fail to reject. All right, so this is bigger than 0.05, so I fail to reject. That means that I accept the hypothesis that residuals are normally distributed. All right, the next thing that we want to check is, do we have autocorrelation between the residuals? Okay, something that we need to have to be able to do certain statistical analysis and regression is that the error between the observed value and the model value needs to be independent for every single observation. So what I don't want to see is, like, if I have, let's say the first time I have an error, like the first residual is big, second one is smaller, 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 smaller as I go through my observations. If I can see a trend in my residuals, some way, some shape, some form as I go through, then there's not an independence aspect. So what I'm trying to do basically is any observation influencing any other observation, and that's what I don't want. All right, there are infinitely many ways that this could, not infinitely, but there are a lot of different ways that residuals or observations could be influencing each other. And we honestly cannot check all of them. What we're going to do, we're going to check for residual autocorrelation. So what we're going to check and see, if I look at the first two, does it look like the third one is influenced? If I check the second and third, does it look like the fourth one is influenced? If I check the third and fourth, does it look like the fifth one is influenced? And this Durbin-Watson test is going to do that for me. And here we just run the calculation. And the Durbin-Watson gives us about 2. And here we're going to do this test also. And we get a p-value that's large, so we fail to reject the null hypothesis. Check the condition number. So here I'm grabbing x again, and then I'm adding on 1s. So there is my x. And here we're pulling off the eigenvalues off after doing some matrix multiplication. And this line of code, this is how we calculate the condition number. And it's a condition number of about 27. Okay. Well, let's, now that we've computed all these, let's go ahead and double check this. Let's see. Do we remember this? Do these look good? Do we like these? Well, condition number of about 27. All right. And here, all right, we didn't compute the p-value for this test, but here it is. Failed to reject the null hypothesis. Here's that Durbin-Watson calculation we did. Kurtosis, all right, all right. Skewness, same value. Here is our omnibus test, the statistic and the p-value. And remember that we had 0 inside this confidence interval. So, if we were worried about, if we had a reason to worry about the intercept, we would, honestly take it out and replace it with 0. So there would just be a slope in the model, but that's very rare in most situations. Here, we do not see 0. 0 is not in this interval. Therefore, we can conclude that tobacco is statistically significant. All right, and that's all I've got. I hope this is informative. I hope this is helping you get a feel. If this feels like a lot, it is a lot. If this feels like you're drinking from a fire hose, yeah, you're drinking from a fire hose. There's a lot going on here. One of the things that we need to do first is just get used to the terminology, get used to being exposed to this way of thinking. If you feel overwhelmed, don't sweat it. What we're going to do for the homework, you're going to take your data, you're going to calculate much of these things, and then you're going to go through and reach conclusions and tell me what's going on with your data and your model. I hope you're doing well. I hope coronavirus is not getting you down. Take care and goodbye.